So now that you've understood monochlorination, let's look at a variation on the last problem. What we have to do here is we have to find out the number of possible monochlorinated products of 2-methylbutane in the presence of sunlight. What you should remember, and what is also the first step as we said last time around, is you have to first draw out the structure of 2-methylbutane. If you are unable to do so, this is the right time to go back and revisit naming of carbon compounds so that you can at least solve questions like these. So Gopi, let's try drawing its structure as such.
Yeah. First, the structure of 2-methylbutane is this. Now in this question you are treated this with chlorine in the presence of sunlight and you are asked to find out the number of possible monochlorinated products.
So Cl2 is in excess.
Yeah.
Okay.
You have taken this in excess. The first thing here is what kind of free radicals you will get as an intermediate that you have to find out.
Okay. So let's draw out the possible intermediates.
First, if the hydrogen is abstracted from this carbon, you will get a free radical here.
Okay.
And if the hydrogen is extracted from this carbon, you will get a free radical here. Now, if a hydrogen is extracted from this carbon, you will get a free radical here. And similarly, if it's extracted from the fourth carbon, you will get a free radical here. Now, you have to see this. If it is extracted from this, you will get the same compound as the before one. See, these two are the same compounds.
Okay, alright.
Now the thing is, it's not over here. You have to find out if there are any possible optical isomers for this. I mean to say that since this free radical is planar, Cl can attack above from it or from below it. So as a result of it, you may get two products for one free radical.
Alright, so how will we go about solving that then?
Yeah, I'll tell you that. For first compound, you will get chlorine here.
Okay.
And for this, you will get chlorine here.
Okay.
And for this, you will get chlorine substituted here.
Okay.
And for this, you will get chlorine here. Now see if there are any possible chiral carbons.
Okay.
A chiral carbon is a carbon which is bonded to 4 different molecules.
Four different
groups. Yeah.
Alright.
Now see, this carbon is chiral because it's bonded to 4 different groups.
Okay, so there's a hydrogen, there's a methyl, there's an ethyl
and chloromethyl.
Chloromethyl, alright.
Yeah.
So that's going to have an optical isomer.
Yeah.
Okay.
2 products are possible from this.
Okay.
Now from this, you can observe that only one product is possible because
it's not chiral.
Yeah.
It has 2 methyl groups, right?
Yeah.
Okay.
And from here also, you will get 2 compounds.
Yeah, because it's chiral again, similarly.
Yeah. And similarly from here, you will get only one.
Because there are 2 hydrogen groups as such, so it's not chiral. Alright.
So the number of products possible are 2 plus 1 plus 2 plus 1, which is 6. Now, I want you to find out how many fractions are obtained when this is subjected to fractional distillation. Now, for this, you have to recapitulate your general organic chemistry topic. Go and see what are the properties of enantiomers.
Okay, alright. So what we've learned in this question, or what we need to be very careful about, is it's very simple to first draw out the structure as we did. That's the first step. After the structure, we draw the free radicals. This is the second step. This is where you also have to be careful if 2 free radicals are pretty much the same compound. Then once we found out the free radical as such, we are going to attach a chlorine to each and every one of those free radicals. But we're then going to see if that attachment of the chlorine atom makes any of the carbon atoms chiral. Because if that does happen, we're going to have an optical isomer as a result of it, and it'll be an entirely different product. And these are the kind of trick questions which IIT JEE also brings about, because they will give you options of 4, 5 and 6 in the examples. And if you do not remember that there can be optical isomers, you will tick the wrong answer, you'll get your -1, and too bad. So be very, very careful about identifying optical isomers, especially in these cases, because these are all planar compounds as such. Alright, so let's move on to the next question. Now that you've studied most favorable monochlorination and the types of chlorinated products that can be formed, let us try and look at a more conceptual problem. What we have to do is explain why C2H6 and C2D6 react at different rates with chlorine in the presence of sunlight. We also have to explain the rate of any one of these with the isotopes of chlorine as such. So, Gopi, what's the way we should go about and approach this problem?
So, first write down what's being asked.
Okay.
C2H6 or C2D6, they are made to react with chlorine in the presence of sunlight.
Okay.
So this question can be answered only if you know the mechanism of it.
Alright, so the mechanism first involves the cleavage of Cl2?
Yeah, it is called the initiation step.
Okay.
Cl. Now you get a Cl free radical.
Okay.
Now in the propagation step, what happens is Cl free radical will act upon, in the first case you will get one radical, and in the second step, in the second case, it cleaves CD bond, you will get one more radical.
Okay, and what is this step called?
This is the propagation step.
Okay.
We call it as a propagation step. Now, as experimentally observed, this is the RDS step for a free radical substitution.
Okay.
So, if you observe, the rate of a reaction will depend on the rate determining step. So, in the rate determining step, the differences between these two reactions is that in the first reaction, you are cleaving a CH bond, whereas in the second reaction, you are cleaving a CD bond. So, the reason not being very clear, it is observed that for in between isotopes, as the number of neutrons increases, the bond strength also increases.
Okay.
So, as a result of it, CD bond is stronger than CH bond.
So, therefore, we will have to expend a greater amount of energy in trying to break a CD bond as opposed to a CH bond.
That is, the second reaction requires more activation energy as it involves break of a higher energy compound.
Okay.
As a result, rate of reaction for C2H6 is greater than rate of reaction for C2D6.
Oh, interesting. Very simple, isn't it? So, how about we look at the second part of the problem, where instead of just chlorine, we were using an isotope of chlorine as such?
The isotopes of chlorine are Cl35, Cl36A.
Okay.
So, in the first step, you will get, in the first case, Cl free radical 35 and Cl free radical, or 37 Cl free radical, or 37 Cl free radical. But
so that is
35, sorry.
Okay.
And if you observe, this is not the rate determining step.
Okay.
So in the rate determining step, if you take any one, you're gonna cleave only CH bond or CD bond.
Right, so doesn't make much of a difference, does it? Alright, so interesting. So what we observe as such is that a Cl bond breakage, by virtue of not being the rate determining step, has virtually no impact on the rate of the reaction. So you can use Cl35, you can use Cl36, you can use Cl37, and what you will pretty much get is the same rate of the reaction for the entire thing, because the rate determining step, as we said, is the propagation step, not the initiation step. So by changing the initiation molecule, we bring about virtually no change in the rate of the reaction. Obviously, the compound that's formed at the end of it is going to be different, but the rate of the reaction does not change because of a change in the compound being used for the initiation step, but it does change the moment we talk about the propagation step as such, and that's the important takeaway from this question. So let's move on to the next question. Question number 5. Though I2 has lesser bond dissociation energy than Cl2, why is the former less reactive than the latter towards the free radical substitution of alkanes? So Gopi, what do you think is the reason?
In the free radical substitution, in the first place, consider X as an any like chlorine, fluorine, any halogen atom. We supply energy to it in the form of sunlight. Now this dissociate to give X radical and X radical. Now in the second step, if you see, whenever an X radical is bonded to an alkyl radical, suppose say ethyl radical, you get ethyl halide. Now in the first case you are inputting energy to it, whereas in the second case energy is being released from this.
Okay.
So in the first case, energy required for fluorine is greater than chlorine, is greater than bromine, is greater than iodine.
So this the first step favors iodine over chlorine.
Yes.
Right? Okay.
This is because for the fluorine being very small size, extent of overlap between the orbitals is very large and therefore it's very strong.
Okay.
The same reason applies for the second case too. Energy released in the case of fluorine is greater than chlorine, is greater than bromine, is greater than iodine. Remember, the first case is energy that is supplied and the second case is energy that is released.
Okay, so the first case is benefiting iodine while the second case is benefiting chlorine.
Yes.
Okay, so how do we come to an answer then?
Now energy released in the second case is more than the energy that is absorbed in the first case.
Okay, so consequently chlorine will have a comparative advantage over iodine as such.
Yes. And combining these factors, you get energy released for fluorine is for chlorine is greater than for bromine is greater than for iodine.
Alright.
Now one more thing you have to, this is very analogous to the solubility of metals. If you see any metals like sodium, potassium, anything, sodium, potassium, lithium, as you know that as the size increases, the solubility of it decreases, and as the size increases, the metallic bond decreases. So as a result of both the factors, solubility for smaller ions is very much greater than the solubility of larger ions.
Alright. Discuss in detail the nitration and sulfonation of alkanes.
Yeah. First, in the nitration, alkane, when treated with fuming nitric acid, you'll get a mixture of products. The reason behind it is this reaction occurs only at a high temperature, and at this high temperature, CC bond cleaves away, giving a mixture of products. For example, I have taken propane here. When I have treated with fuming nitric acid, you'll get NO2 here, or you may get NO2 here. You may get one C bond cleaves, or even in this way you get a mixture of products. But the case is not the same for neoskeleton alkanes. Experimentally, it is observed that for neoskeleton alkanes, this is not going to be the product, and the product is CH3COOH.
Would you care to explain to our audience what are neoalkanes?
Yeah. Neoalkanes are nothing but, see, if you have this branch, it is called iso. If you have this chain, it is called a neoskeleton alkane.
Alright. So these are the is this the entirety of all the products that we get?
Yeah.
So should we move on to sulfonation now?
Yeah.
Okay. So let's look at sulfonation.
But the case is not same with sulfonation, because not much high temperature is required for it because of its more reactivity.
Okay, so H2SO4 is more reactive than HNO3. So the temperature used for nitration is much higher.
Yes.
Okay.
For example, I take propane, treat it with sulfuric acid, you will get either this one or this one. This we call as alkane sulfonic acid.
Okay.
Not just this one, you may call this one also
as alkane sulfonic acid.
Yeah.
So we will not have any cleavage of the carbon-carbon bond in this, and it's fairly straightforward.
Yes.
Okay. So now that we're clear with the concept, I think what we need to keep in mind is two particular things. One is with nitration, the temperature is really high, so cleavage of the carbon-carbon bond can also occur, while the same does not happen with sulfonation because the temperature utilized is less. It's also because H2SO4 is more reactive than HNO3. The other thing we've learned is, especially in the case of neoskeleton alkanes, when we react them with fuming HNO3, what we actually end up getting is an acid as opposed to the expected compound.
Yes.
Right? So with this, let's move on to the next question. Question number 7 is fairly straightforward, where we are given a particular compound. There are two reactions that take place and you're expected to predict A and B. So Gopi, how do you think we'll go about this?
First, you need to know the difference between these two reagents. First is lithium aluminum hydride in presence of E2,2O, and second one is sodium borohydride in presence of methanol. If you observe the solvent in it, you are using an ether solvent here, and here you are using alcohol solvent. Now this is polar protic and this is polar aprotic.
Okay.
If you revise alkyl halides, then you will come to know that in the presence of polar protic solvents, you will proceed through SN1 mechanism, and in the presence of polar aprotic solvents, the reaction proceeds through SN2 mechanism. First, for the lithium aluminum hydride, it's both lithium aluminum hydride and sodium borohydride supplies hydride ions, that is H- ions. Now this is a very strong nucleophile. Now this attacks on the first Br molecule. Now CBr bonds cleaves away and you will get CCBr. If you see, if we proceed this reaction via SN1 mechanism, first CBr bonds cleaves away and you will get carbocation. But primary carbocation is not stable, so this intermediate is not formed. As a result, this reaction won't occur.
Okay.
So, for the first case, that is lithium aluminum hydride, you get A is equal to CCH, and for B, no reaction.
So as you can see, we've used two particular solvents. You need to be very careful about what kind of the solvent is when you're using a particular catalyst as such, whether it's polar aprotic or polar protic, and consequently whether if it's going to be an SN1 mechanism or an SN2 mechanism consequently.
Lastly, I want you to try one more thing. What if I change the alkyl halide? I mean, if I give isoskeleton alkyl halide for the reagent NaBH4 and ethanol, what would be the product? Will the reaction occur or it won't occur? The answer is reaction occurs. Now I want you to refer your alkyl halide chapter and find out the answer for it.
As to why it occurs. The solution is also provided to you in the manual that is given with you, so you can have a look at that if you're unable to find the answer for yourself.